Hello everyone. Today I will discuss about my work on exposure background duality in the search of neutrinoless decay, which is published in 2020. And here is the outline of my talk. I will go through the briefly about the neutrinoless decay and its related basic formulation, and the current status of and projection of different mainstream experiments. I will discuss about it, and the discovery potential, the statistics which we have developed, the theme of current work for the providing the required sensitivity, and we have selected a model for removing the theoretical constants. I will discuss about it, and then I will come to my results and discussion, which is in terms of required sensitivity, in terms of exposure background, limiting irreducible background, and finally the conversion of these sensitivity the realistic configuration. Then I will lastly I will summarize my talk with some future prospects. So we know that the double beta decay is a second order very weak process, and it is only detectable if all the first order beta decay processes are energetically forbidden or not allowed. So in standard model, basically it is a conversion of two neutron into two proton with the immersion of with the emergence of two anti-electron neutrino and two electron. So it can be observed. It can be observed in several isotopes, a number of around 30 isotopes. Of them, some are experimentally feasible, and of them, their decay spectrum is shown for almost 10. And in case of germanium, for example, in case of germanium, the most probable transition from the ground state to the with zero spin to the selenium with Q value to around 2039 keV, but it has also possibility which are very rare and not observed yet to go through the decay for higher states of selenium. So, but double beta decay also leads us into a very physics-wise challenging and fruitful channel for which is called as neutrinoless double beta decay, which is forbidden in the standard model because of in this process we can see that the electron number violate in 2 units, and it is very rare. It has never been observed, and yeah, it is a beyond standard model process, and it provides the nature of neutrino, which would be the if it would be observed, then it would be Majorana nature, and it provides the mass of Majorana neutrino. The signature of this process would be a monoenergetic peak at the Q value of the decay. In this decay, the half-life of this decay can be calculated by using the number of observed events and the detector mass, detector mass with the lifetime, and also the lifetime. The conversion of this half-life into the effective mass of Majorana neutrino involves some theoretical parameters like phase factor, accelerator coupling constant, and nuclear matrix elements. These of them, the phase factors are exactly calculable and calculated, and but there are several models for the calculation of effective for the calculation of accelerator coupling constant and nuclear matrix elements. So and effective mass of M beta beta can be is like this, where UEI is the nuclear maximum matrix elements, and alpha beta are the Majorana phases. So and here is the current status of the mainstream experiments. Of them, the Cambridgian have provided up to now the best limit in terms of effective mass of Majorana neutrino. In future, the experiments are mainly their first goal is to cover the inverted hierarchy, and also to, if in the absence of the signature of neutrinoless double beta decay, then they will go towards the normal hierarchy also. In an experiment, the background can be predicted via the simulation, and this predicted error background can be continuous as well as a real number. However, only integer counts can be observed in an experiment, and most of the experiments are going towards the very low background. That's why the Poisson statistics become a reasonable choice, a good choice to handle such background, low background, and as well as real processes. We have developed to provide the strength of signal corresponding to given background, which is shown here in this figure. On the x-axis is the expected background in counts as well as expected signal, corresponding signal in S0. So we calculate the number of observed events, total number of observed events at the 3 sigma level, and then with 50% probability. And along with this scenario, so in this work we have selected this scheme, 3 sigma excess over background with 50% probability, and also here in this case we have given the we have also calculated for the further more robust discovery potential. So, and we can see that in the background free scenario, we require at least around 10⁻³ counts, and with a signal strength of 0.69. So we have developed these statistics, and this is the theme of current work, to move with this the above selected 3 sigma discovery potential statistics. So to provide the required sensitivity in terms of exposure and background to reach the following target sensitivity, in which the most conservative scenario would be to cover the inverted hierarchy as well as the normal hierarchy. Of course, in the absence of the signature of neutrinoless duality, the experiments must need to go towards the normal hierarchy. So we have selected these as our target sensitivity to provide the requirement in terms of exposure and background. We have selected to convert the half-life from into m-beta-beta. There is an uncertainty in terms of requirement in terms of for the nuclear matrix element as well as accelerator coupling constant. So we have selected a model in which in this figure, from this figure we can understand it. On the x-axis it is the square of nuclear matrix element, geometric mean of matrix element, and on y-axis it is the phase factor multiplied with the accelerator coupling constant. So we can see that there is an inverse correlation between the phase factor as well as the square of nuclear matrix elements. So and for a given constant effective mass of mononeutrinol, their decay rate for us is similar for all the isotopes. It means the neutrinoless double beta decay, theoretically it is there are no favored isotopes for neutrinoless double beta decay. So following these three this theoretical constant, this model, and the target sensitivity using this statistics in terms of 3 sigma 50% discovery potential, then we have calculated the required sensitivity. In this figure, on x-axis is the background index in terms of counts per full width of next ton-year, and y-axis is the exposure in terms of ton-year. So currently the best background achieved is by the GATA, which is around 2 counts per full width of next ton-year. And in order to probe the inverted hierarchy by the next generation experiments, which are targeting to have the 10 ton-year to cover the inverted hierarchy, they must need to reduce their background by order of 100, and also the future projects are also aiming towards in order to probe the inverted normal hierarchy, they are targeting towards decreasing the background of the order of 10⁻³. So, and here the blue line shows the entrance of first background for a given exposure in full width of next region of interest around the Q value. So we can see that this would be the preferred hardware specification space for the future experiments. And in the absence of any background at 3 sigma discovery level, the experiments needs at least 1.7 ton-year of exposure to cover the inverted hierarchy, and 550 ton-year experiment, 50 ton-year exposure to cover the normal hierarchy. In the absence of any background, we need at least just one event which can be claimed for the 3 sigma discovery. So at the 3 sigma discovery, in case of 3 sigma discovery level, for becoming the background free for the next generation of experiments, their background needs they can probe up to this much around. They can start entering towards the normal hierarchy by reducing the background towards the order of n-4, and to cover the inverted hierarchy, the background should be around the order of 3 times 10⁻⁴, and to cover the normal hierarchy, the background should be 6. Of course, achieving this background is challenging, but it would reduce the requirement in terms of the very costly exposure, which is around 500 ton year of exposure. And yeah, and in the presence of higher background, experiments will need to have the even more than 1,000 ton year of exposure. So towards going to coverage of inverted as well as normal hierarchy, the experiments need to face the challenge from the irreducible background from 2 double beta decay, which can only be reduced by having good energy resolution detector. Because a worse resolution means we have larger region of interest around the Q value. A larger region of interest means more and more 2 background contamination in that region of interest. So to become at the background free level, become background free from 2 the experiments need to have the energy resolution of the order of 0.3 to 0.9% for the inverted hierarchy to coverage of inverted hierarchy, and to cover the normal hierarchy, their energy resolution should be 0.1 to 0.3%. Currently, Myrona have achieved 0.12% full width half-max energy resolution, at which the background is from 2 is of the order of 10⁻⁻10. It means they are almost free from it. Of course, the numbers which I just stated, they need to be in the calculation of these numbers. The sensitivity, the isotopic abundance, external efficiencies have been chosen to be 100%, and to convert these numbers to the realistic scenario, all these sensitivity in terms of exposure as well as background needs to be converted from by using this formulation and having the realistic scenario of isotopic abundance as well as efficiency. And we have also chosen the unquenched value of free nucleon value of Ga, which is 1.27. Here in this figure, I have shown the variation of accelerator coupling constant, which varies in the range of 0.6 to 1.269 with the weight factor of exposure due to the variation in Ga relative to the free nucleon value Ga equals to 1.27. So we can see that in the presence of nucleometric uncertainty from different models, the exposure should be scaled with this weight factor, and so the requirement in terms of exposure and background will be more and more robust in the presence of a realistic scenario. So now this is the summary of my talk. So the coverage of normal hierarchy would require large and costly exposure, and the reduction in background would be playing increasingly significant role especially for the normal hierarchy, because the same exposure can be probe a longer half-life as well as smaller m beta with decreasing background. And at the unquenched value of Ga 1.27, the coverage of inverted hierarchy from the experiments requires at least 1.7 ton year of exposure, and to cover the normal hierarchy, we need at least 550 ton year of exposure. Currently, we have worked out on the counting statistics, and right now we are working on the putting the energy information in terms of best fit maximum likelihood, and we are working on it. Thank you.